All right, in this podcast, we're going to talk about reduction potentials, specifically in the context of being able to look at a galvanic cell and determine which species is going to be oxidized and which species is going to be reduced. All right, so previously I had shown you this copper zinc galvanic cell, so I just wanted to remind you. So if I were to look at that cell, how would I be able to determine which metal is going to be oxidized and which is going to be reduced? Well, in order to do this, we must look at what are called reduction potentials. Basically, a reduction potential assigns a value to the tendency of the given half-cell reaction to occur as a reduction as compared to a standard hydrogen electrode. So basically what they do is they took all the different metals and they measured the voltage produced against a standard hydrogen electrode. So hydrogen is assigned a value of 0, and then everybody else is based off of hydrogen. The greater the tendency for a substance to be reduced, the higher the value. So the higher the reduction potential value we get, the more likely the substance is to be reduced. All right, so reduction potentials, you'll commonly see them abbreviated this way. By convention, all of our half-cell potentials are going to be given to us as reduction potentials, even though they might not all be very likely to be actually reduced. And all of these values are for half cells that have a concentration of 1 molar or at a pressure of 1 atm and a temperature of 25 degrees Celsius. All right, so here is an example table of reduction potentials. Notice that here is the hydrogen electrode, has a value of 0. And then everybody that is a better, is more likely to be reduced is up here than hydrogen, and anybody that's less likely to be reduced is going to be below hydrogen. Okay, so again, the farther up you get, so the more positive your number gets, the more likely that it's going to attract electrons or be reduced, gain electrons. And then the opposite is true. The more negative your number gets, the more likely it is to lose electrons or be oxidized. All right, so which species is going to be reduced? So when you have two metals, you want to look at their reduction potentials. The substance that has the most positive reduction potential value is going to be the substance reduced. The other substance is going to be have a more negative number, and therefore it will be oxidized. So because they're all written in terms of reduction, the smaller value, that substance equation needs to be flipped. And because we flip the equation, we also need to change the sign of our reduction potential. Okay, so back to our copper zinc half cell. Okay, so we know that I pulled out the reduction equations and their actual reduction potential values for both zinc and copper. Because copper has the highest positive value, so the most positive value, it's going to be the one that is reduced. So this equation is written appropriately. All right, now because zinc has the lower value, it's actually going to be oxidized, which means I need to straight reverse this equation and make this into a positive 0.76 volts. All right, so here I went. So I was able to flip our equation for zinc, our oxidized, left the copper one alone. And then I had to change my value for zinc. I had to make it a positive value instead of a negative value. All right, so what is actually happening here? Okay, so we definitely determined that copper is going to gain electrons, okay? So let's think about what we got at this point. So over here in solution, we have copper 2 sulfate solution. So we have a bunch of coppers. Okay, we also have sulfates. They're spectator ions. We will talk about them later, but not at this present moment. All right, over here we have zinc sulfate. So in solution, we have all these little Zn2 pluses. Okay, and in an ideal world, there are equivalence amount of each, blah, blah, blah. Okay, all right, now on our actual electrodes are just the normal little elements. So we got zinc, elemental zinc, so oxidation number is 0. And then over here, we have elemental copper on this electrode. And it gets kind of hard to see going up that way. Okay, so we know that copper is being reduced. That means copper is gaining electrons. Okay, so all of these little coppers right here, these copper 2 pluses, they are getting electrons off of the copper metal. Okay, so they're getting these electrons, and as they get electrons, they are turning into elemental copper, right? So I'm going to rewrite our equations just so we all remember what's going on. Okay, so they are turning into elemental copper. Elemental copper is a metal. So all these little coppers in solution, they are attaching to this copper electrode, okay? Now, zinc, on the other hand, zinc is being oxidized. So that means zinc is losing electrons. So, dang it. So this was our equation. All right, 2 electrons. Okay, so what's happening here is our zinc metals, they are losing electrons, so they are sending the electrons through the wire, okay, towards our copper solution. Okay, so this is where our extra electrons are coming from that are grabbing all of our copper 2 plus ions out of solution and basically they're hooking on to this copper electrode. So my copper electrode is increasing in mass. Okay, so it's getting more and more and more coppers attached to it. Okay, over here, as these zincs are sending electrons through the wires, they are becoming zinc 2 pluses. So they are then falling off of the electrode into solution. So this electrode over here is decreasing in mass. Okay, so that's essentially what we got going on right here. We got an electron flow going from the oxidized species to the reduced species. Reduced species is basically getting the electrons. The electrons are being put on the ions, the copper ions in solution, and then they are attaching to our copper metal, and so this is getting bigger and bigger and bigger. And then over here are zincs. As they are losing the electrons, they are coming off the zinc electrode and dissolving in solution.